Hello and welcome. We are just about to start our webinar at the Orchard OCD Conversations. I'm going to wait a little bit just to make sure we have as many people as possible watching from the start. So I'll give it another minute, see if we get many people joining. And of course, people will join throughout this podcast, this visual podcast, but it'd be quite good to get as many people as we can at the beginning. So I'll just give it another minute and then we'll start with our next OCD conversations. So just to say to everybody who's joined, we're going to start in about a minute or so. I'll give it about 30 seconds and then we'll start this OCD conversations. Okay, I think we should get going. Make sure all the cameras are in the right place. Okay. Hello and welcome to the OCD Conversations, a series exploring new and innovative ways to treat obsessive-compulsive disorder, from psychedelics to psychotherapy, deep brain stimulation to ultrasound stimulation, as well as repurposed medications and even computer games. I'll pick the brains of the groundbreaking people who are pushing the boundaries, quite literally, when it comes to OCD treatments. We're really privileged to hear from some of the world's leading specialists who are transforming the way we view and tackle a condition the World Health Organization classifies among the top 10 most debilitating illnesses globally, and which affects about 70 million people worldwide. I'm Sean Fletcher. I'm a mental health campaigner. I'm someone who's had experience of OCD in my family. It's affected my family, and I have seen firsthand how debilitating and how destructive OCD can be. Now, last month in the OCD Conversations, I talked to Professor Amy Milton about neurotransmitters, glutamate and GABA, and the work she's doing in her rat models with that. It's well worth a listen. So if you haven't already done so, please do. Today, we continue that theme. So I'm joined by a neuroscientist and psychologist using advanced neuroimaging methods, behavioral and clinical studies to understand and improve outcomes in people with lived experience of OCD. So I'm going to be joined by Dr. Marjan Biria, and let's see if we can get her on stage now. Marjan, great to see you. Really good. I say this every week when we have someone, every month when we have someone on. I press the button and I'm never sure they're going to appear, and you have appeared straight away. So it's really good. Thank you very much for joining us.
Thanks for having me. I'm excited to be here.
Yeah, and we're really excited to hear about the work you're doing. I've mentioned to quite a few people in the OCD community that I'll be speaking to you, and quite a few people, many of them have said, oh, that's really exciting. That's a world first. That's sort of a game changer. So what we're about to hear for the next 45 minutes, hour, it's really exciting. And I feel really privileged to be able to talk to you. So to start with, we're talking about those neurotransmitters, glutamate and GABA. Can you tell us what they are?
So neurotransmitters in general, they're chemical messengers. They are like text messages between the cells in the brain. And glutamate and GABA specifically are the main excitatory and inhibitory neurotransmitters. So glutamate is excitatory, GABA is inhibitory. What that means is that glutamate is like putting your foot on the gas pedal. It increases the activity of the neurons, whereas GABA is like putting your foot on the brake. It reduces the activity. It calms down the neurons. If we use car driving analogy.
Yeah, no, I mean that really explains it, because on the OCD Conversations, we've got people like you who know all about this stuff and who will want to get the sort of meaty detail, which we'll get onto. But we also have people who are like me, we're lay people, and when you explain it like that, it makes sense. So you're in a car, glutamate is the accelerator, GABA is the brake, and that's happening like thousands of times a second in your brain with everything you're doing.
Yeah, exactly.
So what have you found in terms of the imbalance between glutamate and GABA and OCD?
So we have found an imbalance between the levels of glutamate and GABA in the brain in regions that are important for habit formation. For example, anterior cingulate cortex is one of the important regions in the network that is relevant for habit formation. So we found an imbalance between glutamate and GABA, but we also found lower GABA and higher glutamate in this region. The next important thing that we found was that in supplementary motor area, or SMA, we found a correlation, positive correlation between levels of glutamate and how much compulsion someone shows and how much habitual tendencies someone has. And it's really interesting because this link between glutamate and habitual tendencies and compulsions, we didn't just find it in OCD, in patients with OCD, we also found it in our healthy volunteers.
So if you are someone with lived experience of OCD and you are performing compulsions, that's a higher amount of glutamate. There's an imbalance with a higher amount of glutamate than GABA. Is that
so? We didn't find a difference in the levels of glutamate in the SMA, but we found a positive link between glutamate and habitual tendencies or compulsions. So it is true that the more habitual someone is, or the more severe OCD symptoms they have, the more glutamate they have in the SMA.
Oh, so what's SMA mean?
Sorry, supplementary motor area.
Okay, and that's a part of the brain, is it?
So it's up here.
Okay, fine.
Yeah, it
so
helps with.
It's all happening up here. So if you're experiencing compulsions and you're struggling with that it's sort of in this area that this is all happening, top area of your brain.
So it's not. Yeah, I mean, it's not the origin. I don't think we can claim that this is the origin, because there is a network that is involved in habit formation. But SMA and ACC, so anterior cingulate cortex and supplementary motor area, they are playing an important role, and these are part of the cortex. So they are more evolved in. I mean, animals don't have a cortex, and it's a lot more expanded in humans. And so SMA is here, and ACC is a bit lower. It's a bit towards the front. I mean, ACC is a big region. I don't want to go into details of
no, well, that's not what we're here to
neuroscience a bit.
We're here to talk about your findings, and I suppose this is where the work gets really key, and this is where your findings are kind of groundbreaking. I kind of feel like I say that every month we do the podcast. I say groundbreaking, but I am speaking to people like you who are doing groundbreaking things, and this is particularly it's sort of you're at the boundaries of where we're finding things. So how do you measure glutamate and GABA in the brain? And because that's the key thing, isn't it?
Yeah, so we use a specific technique called magnetic resonance spectroscopy. So we use a scanner which is an MRI scanner, looks like an MRI scanner, and you can measure the neurochemical levels in a non-invasive way. I don't know if you could show like some of the images that I have sent to you.
This is sort of the first time I've used this technology on this this platform, so I'm quite excited about this as well. So tell us what we're seeing here.
So I don't know if you can see my mouse, but if I can explain. So in the blue square that you can see, that's anterior cingulate cortex, and in gray you can see an MRI scan of the brain, so that we have a picture of the brain, and on the right side we have the neurochemicals. That's how we can see the signal. That's how we visualize the signal. So the red line is the signal we are measuring. Actually, the red line is the noise, the black line is the signal, and you can see like how good our signal is, because sorry, it's not the noise. You can see how close they are. It shows that our signal to noise ratio is very high and accurate.
Okay.
So if you go to the next slide, then I can show you how glutamate and GABA signal looks like.
Can I just ask you a few questions on that? So the
Sure.
blue box is in the left-hand photo.
Yeah.
So that's an MRI scan of someone side on, and the blue box is the particular area that you're looking at.
Yeah, exactly. And when we do MRS, magnetic resonance spectroscopy, we need to first take a picture of the brain, and then we will place boxes in the regions that we want to measure the neurochemicals. And because the reason we do that is because every brain is different, the same way that every person looks different from another. So we take, to be accurate, we take a picture of the brain, we place a box. This is the box for anterior cingulate cortex, and then we will measure the neurochemicals in that area.
And that's the area that's being scanned. Sorry, just to go on the table.
Exactly.
So the red line, and when you said the black line is the measuring of the GABA or glutamate imbalance, is that the top line you're saying?
No, sorry. So
one.
where we have the red line, there is a black line underneath. So that's
Yes,
how we are modeling, actually, how we are modeling the signal. And yeah.
And so the scan, which we'll get onto, MRI, MRS you mentioned, we'll get onto that in just a moment. That's the MRS is basically measuring that, and you're measuring the imbalance between glutamate and GABA, which is what we're establishing is key.
Exactly. Yeah.
Fine.
So on the right side, sorry.
Yeah. You want me to go on to the next slide, don't you? But carry on.
Yeah. So on the right side we have MRS. On the left side we have MRI scan.
I see. Okay. Sorry. I see. On the left side is MRI. MRS is the right-hand side.
Yeah.
Okay. And for people listening who are thinking, what is MRS? We will explain that in just a moment. This is the next table that you wanted me to show.
Yeah. So the black line is showing the signal for all the neurochemicals we have in the brain. We have a lot of different types, like creatine, NAA. We have many different types of neurochemicals. Each of them, they have a role in the brain. And the reason it has been difficult to measure glutamate and GABA in the past is because glutamate and GABA, so on the left side, we have GABA, that's the red line. And on the right side, we have glutamate in the red line. And the peaks that you can see, the 3 peaks that you can see, they are the peaks for GABA and glutamate. And the black line that you see above that is all the other neurochemicals accumulated. And the problem is when you have neurochemicals that are bigger than glutamate and GABA, they would cover glutamate and GABA. And if you don't have scanners that are powerful enough, they cannot be detected accurately.
So people may have tried this in the past, but they didn't do it strong enough, so that the other neurotransmitters just clouded everything.
Yeah, so people have tried to model them, try to estimate, but because these neurochemicals were covering them and the scanners were not powerful enough to measure them accurately, we didn't have very accurate measures before our study. And I also have to say, in the past, or like in the scanners that were less powerful than 7 Tesla, our scanner was 7 Tesla. I can tell you a bit about it later. In the past, people used to combine to estimate these neurochemical levels together. So they would say glutamate and glutamine are at this level. They couldn't separate them. Glutamine, and GABA are at this level. They couldn't separate them. But it's really crucial to be able to separate them because they have different roles.
And can I just ask what's on the bottom there? My eyesight's not very good there. I probably need my glasses. Don't know. What's from left to right? What is that? What is that time over time?
No, that's the chemical shifts. That's parts per million. Would you like me to explain how we measure them?
I think it would be helpful. I mean, there'll be people who know all about this, but there'll be others who will be thinking, it looks like a chart. I think I get it, but I'm not quite sure what that means. What's the bottom?
So I'm going to explain how we measure this, how MRS works, how the scanner measures the signal, so you can understand what is this. Shall
I show the next picture? Would that be helpful?
Sure. Can you show the next one, but then go back to this one?
Yeah, we'll come back to that. So this is because the top left, that looks familiar. That looks like an MRI scan.
That's exactly an MRI scan. It's not the one that we use. We use the Siemens brand, but this is the picture I found online. So on the left side, we have an MRI scanner, which you can use also to measure the neurochemicals. On the right side, this is me and a colleague. And you can see that we have taken a picture of the brain. And we were trying to place the box in the region that we wanted to measure the neurochemicals in. So when people are inside the scanner, because of the magnetic field of the scanner, the hydrogen nuclei inside each molecule in the ACC, they will become aligned. So imagine them like needles, and each of them will have I don't know how to explain it. They will be, for example, imagine these are needles, and they will be all aligned because of the magnetic field.
Yeah,
and then once that happens, we will, on the computer, we will send a radio frequency pulse, and that would make them unaligned.
I see.
And then we will wait for them, because of the magnetic field, they would need to become aligned again. And then we would wait for this to happen. And that is the shift, the chemical shift that we are measuring.
I see. So in a way, you're trying to mess everything up and then waiting for it all to come back.
Exactly.
That's the bit you're measuring.
Exactly.
When you say the needles, and I'm sorry, I'm sounding like a complete layperson here. What is that? That they are the neurotransmitters, or? Sorry,
no, that might not have been a good example. So that's the hydrogen nucleus.
Okay, fine.
Yeah,
and
the protons.
In our brain.
The protons become aligned or unaligned.
I see. And so you're unaligning them, and when they then naturally form back in the same direction,
exactly,
that's what you're measuring.
Exactly. Yeah, and we have them in every neuron.
I see.
Yeah.
So tell me, and that gives you the level of imbalance between glutamate and GABA, which is where we
exactly. Yeah. So if you go back to the previous slide.
Yeah, that's the one.
So the numbers that you see on the x-axis, that is the chemical shift that we are measuring, waiting for them to become aligned. Yeah.
And so what I noticed from that, so you're saying on the left is GABA, as we can see, the red line is GABA, on the right, the red line is glutamate. I mean, glutamate occasionally seems to follow what all the other transmitters are doing, but doesn't much. GABA doesn't at all. So if you're getting them all mixed up, you are not getting a clear picture at all. I can see that. You need to separate the different neurotransmitters.
Yeah. Yes, exactly. And sorry, I have to correct myself. So it's not the red lines, but the peaks in the red line. You see the three little peaks.
Yes, I see that.
Yeah.
But when the other neurotransmitters are peaking, GABA isn't always peaking. It's not always following the
No, they have different peaks. Yeah.
Yeah. And the same with glutamate. So actually, by not being able to separate them, it's sort of worthless.
Yeah.
But what you were doing was separating the neurotransmitters, that's the breakthrough. That's the new thing that you were doing. So can you tell? You may have already explained it. What's the difference between MRI and MRS? You've mentioned MRS, and MRS is the key thing that you're doing, isn't it?
Yes, it is. Sorry, can I just mention something before answering this question? I mean, I know that there have been studies that have done this, so I cannot say they were worthless, but it's just difficult to estimate them. They are more inaccurate. The findings have been mixed. Some people had similar results to us. Some people had opposite. Some people didn't find anything. It's just more inaccurate.
Yeah.
Yeah.
So when they're accurate, isn't that just luck, or what?
It's hard to claim because the signal to noise ratio is lower, and we know that it's hard to measure these neurochemicals more accurately. Yeah.
Yeah. I mean, it's absolutely fascinating. I mean, it's obviously this is you're leading in your field, and it's very complicated, and I'm sure you're simplifying it with someone like me, but I kind of feel like my brain's going to blow up just hearing all this, but I kind of get it. I kind of get what you're saying. So can you explain what the difference is? Because many people that are watching this will know what an MRI scan is. They may have had one on an injury or something like that. What's the difference between that and an MRS? And then you mentioned the power. I can't remember the unit you said, a Tesla or something like that.
Yeah.
Can you explain what that is?
Yes. So MRI is, I don't know if you want to go back to the first picture you showed.
So this one?
No, the other one.
This one, yeah.
Yeah, so on the left side, we have an MRI. So MRI basically is a picture of the brain. It will show us the structure. It will show us if there are any problems with the structure, if there is loss of gray matter, for example. And MRS, so you can imagine an MRI scan like a snapshot picture of your brain.
Yeah.
And MRS, maybe you can think of it like a blood test. A blood test that is non-invasive. It can tell you which neurochemicals and how much of them are available.
But what's actually happening? Are they completely different processes? Or when we go back to this slide, does an MRI scan look exactly like that?
It's exactly like that. And actually, we have used the same scanner to take an MRI picture. So you can see on the right side, we have used exactly the same scanner. So you can see 4 different, I don't know why we have 4 of them there, but the picture that you can see on the screen is exactly an MRI picture. And we needed to have a snapshot of the brain to be able to find where anterior cingulate is for this specific person, or where supplementary motor area is. And in the same scanner, after we've done the MRI, which takes about maybe 10 minutes, we will use the same software, but a different option to run the MRS. And it takes about 20 minutes. It will. We are still having the MRI scan in front of us, and then we will also see the neurochemicals. The graph that I showed you, we see a similar graph in front of us as well.
Yeah, and going back to this one, so the MRI establishes where you're going to focus your MRS. That's the blue box there, and then you use the MRS on that area of the blue blocks, which then gives you the data that we just saw in one of the other slides.
Exactly. Okay. Yeah.
It's all making sense. Yeah, I get that. So something like this feels like, given that you're saying this is kind of groundbreaking, it's the first time it was done, it's new. It sounds like that takes a long time. It needs a lot of funding. Can you talk us through that side of things?
Yeah. Well, first of all, I would like to thank our funders, Wellcome Trust, who funded our study. It was a grant given to Professor Trevor Robbins for the MRS study. And I also would like to thank the funders who funded my PhD, Mental Health Research UK. Without their supports, this study would not have been possible. So this study took quite a long time, actually. It took about, so the data collection, the ethics data collection, everything took about 4 years. But it was because we also had the pandemic. So there was a pause in between. We could not do any testing. Another reason that it took a bit longer was because we wanted to make sure that the data quality is as best as it can be. So we spent actually 1 whole year just trying to optimize the signal. We did a lot of pilot scans, and the software that I mentioned, we run the radio frequency pulse, like they all use a sequence. I don't want to go into a lot of technical details, but we made sure that the signal to noise ratio, so the amount of signal that we get from the neurochemicals, is much higher than the noise. Because when you have a strong magnet, you don't just measure signal accurately, you also magnify the noise. So we had to be very careful to eliminate the noise. So we spent 1 year on that. So yeah, I guess the data collection took us around 3 years.
Wow, I mean that's a huge project. I'm just thinking about my world. You do a live program, you go in the morning and it's done, and then you're out by the afternoon. So there's sort of the really long project. Yeah. I just wanted to add about the Wellcome Trust, because they've obviously played a key role in that. I think they do really play a key role in for the OCD community. There'll be people watching who probably won't know too much about the Wellcome Trust, but they obviously funded this absolutely groundbreaking research, which is very important. They're also just in addition to that, funding a conference that Orchard, the Orchard charity, are going to be hosting next year. So this is the end of spring next year, where we're bringing together all the sort of great minds around the world in terms of OCD. I'm sure be getting an invite, I'm sure, Marjan, but people from around the world who are doing the sort of work you're doing and other work in for the OCD community. We're going to be bringing them together. I mean, I suppose just thinking about this, I'm into sport. I'm not so much of a scientist, but it's a bit like you think about all the best football teams around the world. We're bringing the best players together, a bit like the World Cup. We're bringing them together so that they will be talking and sharing ideas. Also, people who with lived experience will be at that conference too. So there'll be a chance for everybody other people to be invited. These sorts of things are important. I mean, maybe you could explain, Marjan, bringing academics together who are doing similar sort of work. How important is that to share stuff? Because I can imagine you could all be quite siloed in your own areas and not sharing. Is that sort of thing really important?
Absolutely. I think it is really, really crucial. And, going to conferences like this creates an opportunity for us to talk to each other, find out more about our research. Because when you have more casual chats with people, I mean, obviously listening to each other's talk, having the opportunity to ask questions, but then during the coffee breaks, having the opportunity to have a casual talk, these are the moments that you might come up with groundbreaking ideas for new types of research. And I think for this conference, it's not just researchers, but people with lived experience. And this is really, we really need people with lived experience to give us feedback and ask us questions, because otherwise we will come up with ideas that might not even make any sense or might not even be relevant. So we really need to work with researchers, but also people with lived experience. And I think this opportunity is really, really amazing.
Yeah, I just to add to that, to round that off, thank you very much for the Wellcome Trust, because those are the sorts of things that really make difference. And that's actually really interesting to hear, that it's not necessarily the talks that do it. That's really important, but it's those breakout sessions when people are just chatting casually, when some of these great ideas are founded. So amazing work that the Wellcome Trust are doing for the OCD community. But let's get it back onto your work. You've already, I think you've touched on this. No one else was doing this kind of work in the world when you mentioned Trevor Robbins were doing this. This is a first.
It is the first 7 Tesla study in OCD. There have been many studies before. Maybe now is a good time to talk about what 7 Tesla means.
Yes, exactly.
So 7 Tesla is the strength of the magnets. I did explain to you, like, the magnets creating a magnetic field and the hydrogen atoms becoming aligned and unaligned, and that's the key for measuring the neurochemicals accurately. So the scanners that we use in hospitals, their strength is 3 Tesla, just to give you an idea. And the scanner that we use is almost double as much, so 7 Tesla. And the studies previous to our study, they had used magnets that were 1.5 Tesla or 3 Tesla. So the findings have been quite mixed. And we were the first study using a 7 Tesla scanner. And we were the first study to show both an imbalance between glutamate and GABA, and higher levels of glutamate, lower levels of GABA, and the link between these neurochemicals and habitual tendencies, compulsivity, and also showing the link between compulsivity, not only in OCD, but also as a transdiagnostic problem.
And that, we've had some questions coming in. Please do send your questions in. I'm sure many people are watching thinking, I've got a burning question and I haven't answered it. So please send them in. Margarita has messaged in on, I think that sort of ties in with that. So is the glutamate increase particularly relevant for specific OCD subtypes rather than others, or not really? Do we have any evidence about this? I think what Margarita's saying, you may be able to correct me, that if you have a certain type of OCD, maybe it's contamination OCD, is that different? Does that display differently with glutamate and GABA imbalances to, say, Puro or something like that?
Yeah, we haven't found any evidence of that. So people that we have studied, we found this increased glutamate, reduced GABA, and the imbalance amongst all people with OCD. So we haven't found any evidence that the glutamate increase is specific to subtypes, or the relationship between glutamate and habit formation, for example, in SMA, is specific to a certain subtype.
Yeah,
it seems to be a more general
okay. How did you know in the first place to search for glutamate and GABA levels in people displaying compulsive behavior? Did you have a tip off? Do other people doing research and they sort of establish this, or did you? What was the sort of the spark that made you look for that?
So, as I mentioned in the beginning, glutamate is the main excitatory neurotransmitter in the brain. It means that it sends messages to other neurons to increase their activity. So there have been studies showing increased activation in OCD in regions that are important for OCD symptoms. So that was one type of hints that we should be studying glutamate. And if you have increased activation, it means we could suspect that there is increased glutamate but reduced GABA, because if you have increased GABA and increased glutamate, GABA would probably control glutamate and not allow it to increase the activity. So that's why we hypothesized that we would find increased glutamate, reduced GABA in regions that are important for OCD symptoms. But there have been also other types of studies, like animal studies, genetic studies, about the glutamatergic abnormality in OCD.
So was there a moment where you weren't sure and you got the results? I'm just sort of have visions of the day that you discovered that, there is an imbalance, or was it a slow process? Was there sort of a eureka moment?
So we started seeing a trend even with a smaller sample size. And when we increased the sample, the trends became very significant. But I do remember the moment that I was analyzing the data, and exactly, like, I was looking outside and I was thinking, did I make a mistake? Is that real? And I needed to talk to my PhD supervisor, Trevor Robbins. And I had to repeat the analysis because I thought, is this just a fluke? Is that a mistake? Mm-hmm. And Trevor reassured me, no, this is correct. And yeah.
I mean, the way you're explaining it, you're smiling, because obviously that's a really key moment, and we should all be smiling because it's a key moment for anyone who has any sort of experience of OCD. What do you do as a scientist? Do you sort of go around, drinking champagne, or do you sort of then are there lots of other tests you have to do to verify that?
I did repeat a test, and I think we might have gone out with my husband for dinner or drink, but I cannot remember. I was also exhausted, both because I had worked hard and analyzed the data, but also because of how much excitement I had. But we did celebrate.
3 or 4 years work. I mean, you deserve to celebrate. So tell me, what parts of the brain, I think you might have actually alluded to this, what parts of the brain are the imbalances most prevalent when someone with lived experience of OCD, when OCD is really, taking hold?
Yeah. So as I mentioned, the OCD symptoms, like, we think that the OCD symptoms might arise from an imbalance between the habit system and the goal-directed system, and there is a whole network running these systems. But we studied anterior cingulate cortex and supplementary motor area because we thought these are two very key regions in the network.
These are at the top.
Exactly, here and a bit, yeah.
Okay, then these are the parts of the brain that animals don't have, or have very small versions of, and we as human beings, that sort of separates us from.
Yeah.
And that's where this is happening. Does it give us more of an understanding of OCD? What does it mean for our understanding of OCD?
Yeah, I guess I've spoken to some people with OCD, and they have told me that they are relieved to hear that OCD is not their fault, having too many thoughts or not being able to control their behaviors. OCD seems to be a neurochemical problem, and
yeah, that's actually, so that's sort of saying it's not you, it's the thing, it's the neurotransmitters. Yeah, I get it.
Because OCD can be really debilitating, impacting not just the person, the whole family. And a lot of times people feel guilty because they can see the negative impact it has, but it's hard for them to make a change on their own. And hearing that there is a chemical imbalance in the brain, it provides some relief for many people.
Yeah.
And I guess the second thing is it highlights again the importance of the habit system in OCD. And it really there have been many studies about the habitual and goal-directed system, but seeing a link between having kind of a neural mediator for the habitual tendency, that is the first time you're showing it, and I mean in terms of the neurochemicals.
Yeah, I mean, what does it mean for high habitual tendencies? What does these findings mean?
So habitual should I explain how we've done it in the study, or should I define what habitual tendencies
Can you do both? Can you do both?
Sure.
What are high habitual tendencies?
Yeah, so maybe I define what they are and then I'll explain how we did it in the study. So habitual tendency means we do things in an automatic way. And this is really crucial. We cannot imagine learning everything for the first time. Imagine you're going to work for the first time. You have to remember where you're going. You need to look at all the streets, and you need to be really vigilant and present. Can you imagine doing that every time you go to work, even after 1 year, 2 years? So when you do something many times repeatedly, it becomes a habit. Like maybe like after 3 months, you can be on your phone, you can be doing other stuff, you can be thinking about other stuff, and you still manage to get to work. Sometimes there is something called a slip of action. You might want to stop the habit. For example, you have a dentist appointment, and the route to your dentist is halfway through the route that you take to your work. And you want to go to the dentist, and then you end up finding yourself in front of your office building. And that is a slip of action, because it is so habitual that even one time that you don't want to go to work, you want to go to the dentist, you end up taking the same route. Yeah. So habits are extremely helpful, but they become a problem when there is perseveration, when they are rigid, and that is what happens in OCD. So habitual tendency means that you know something else is better for you, and that is the goal-directed behavior. If you see something is better, you change your behavior. But habitual tendency means you still do what you're used to, what is automatic. And there is a deficit in the habit system if you still stick to what is automatic and habitual instead of what is better for you, what is goal-directed. I have to say, I did say there is a deficit in the habit system, but it might be that there is a deficit in the goal-directed system. And because the goal-directed system is not working properly, the habit system takes over. Or it could be one level higher. The arbitration system, the system that decides whether for this action we need to use the habit system versus the goal-directed system. So if the arbitration system doesn't work properly and it keeps favoring the habit system, then we might see the same thing. Now, coming back to our study, the way we tried to study the habitual tendency was using a computer task that it's called contingency degradation task. Actually, it's a very elaborative task, but for the purpose of our neuroimaging study, we really simplified it. Basically, people will see a picture of a vase, and they have to press on the space bar to put flowers in the vase. And then there are different blocks. So sometimes you will receive a reward. It would be you will see coins, like it is monetary reward. So when there are some blocks that you get the reward by pressing the spacebar. So if you are goal-directed and if you want the reward, you need to press the spacebar often. And when you manage to put the flower in the vase, you get the money, you get the reward. And over time, after many trials, this tends to become habitual, because towards the end, there is a block where you will get the money regardless of what you do, regardless of your action, whether or not you press the spacebar or not. And we know that people with OCD will learn. It's not a problem of learning, because they will learn the consequence of this action, but still they're not able to stop pressing. They keep pressing on the spacebar.
So they're going to get the coins anyway, but they keep pressing on the spacebar.
Yeah. So in our study, we didn't find an increased pressing in the OCD group, but as I mentioned, because we didn't use a very elaborative task, there have been other studies in drug addiction and in OCD, and when they use that very elaborative task, which is a lot more difficult, they have shown significant differences between people with OCD and healthy volunteers. In our study, so we have measured the habitual tendency. The habitual tendency is pressing the spacebar when you don't even get any rewards for it. It's not goal-directed, it's just because you've used to pressing it in the previous trials. So we have found a correlation between the neurochemicals in the brain in both anterior cingulate cortex and supplementary motor area, and this habitual tendency.
I see. There's a question from Nick Siro. Hi, Marjan. You also published a paper showing a link between excessive checking and the glutamate GABA balance. That's what you're talking about now, is it? Or is that
no, this is the habitual tendency, but that is something else. Yeah, thanks, Nick, for the question. Yeah.
Can you explain a bit more about that work you did?
Yes. So we wanted to have a measure of checking in an experimental setting, because having questionnaires, it's very subjective. So first, before doing the study, I had to design and develop a checking task to be able to measure checking, compulsive checking in a laboratory setting. And we did find that people with OCD, they checked a lot more in the task. And that was when they were less confident, when they were more anxious. And we also found that this type of checking was correlated with this glutamate and GABA imbalance in anterior cingulate cortex. And it is probably because they were anxious and they had less confidence, they felt the need to check more. And they were feeling conflict, they were checking more, but they still were not confident, and they were feeling a conflict. And there is something called error monitoring, and that is actually one of the functions of anterior cingulate, this constant feeling that something is wrong. And so we think that's why anterior cingulate was engaged. And we know that anterior cingulate activity is related to error monitoring in OCD. And we think that's why we found this relationship.
So going back to your MRS study, I'm just thinking, I'm putting this together and thinking, then doctors in the future could just measure brain chemicals to measure OCD. Is that a thing, or am I jumping a bit too far ahead?
I wish we could. But it's really important to say that the levels of glutamate and GABA can change in the same person for various reasons, depending on time of the day, time of the month for women, and also if they've had coffee, if they had smoked, but also there is individual variability. So for our study, to make sure that we get rid of these issues, we had to use many people and average the signal. When we average the signal, we average out these types of noises, if that makes sense. So I have received so many emails from people with OCD, from their families, asking whether it's possible to take an MRS scan of their brains to confirm the OCD, but also for treatment purposes. But unfortunately, that's not how we can use MRS.
What about if I know this would be too expensive to do, but if you say measured my brain every day for a month, then you get a pattern of, if I'm smoking, if I'm not sleeping well. Could you do it then? Obviously, that's not probably, we couldn't do that on the NHS because it would cost too much money, but that's how you would be able to do it.
Yeah, exactly. Yeah.
Basically building up a pattern of when my glutamate and GABA is high and low, or the balance is right or imbalance.
Yeah,
and then from there you could work out.
Yeah, I think maybe if we had thousands and thousands of, or maybe more, maybe millions, I don't know, like of brain scans from people, and we had literally every other information from them, maybe then we could predict, okay, when we take this scan, we have the information of this person, and we have modeled based on thousands or millions of brain scans that probably this person has OCD. But at the moment, we don't have that. And it's very unlikely that we can do that because it's hard to control for every variable.
So if we had a lot of brain scans, I mean, I'm just thinking about AI. Can't AI just replicate what other brain scans, as in it could look at 20 and then say, well, actually 20 means that 1,000 would look like this. And then from that, you could go on and then start to build a pattern of what people's brains are. Am I just jumping to conclusions that I shouldn't be?
Yeah, I'm trying to remember the phrase that we use in in machine learning and AI when you have a small sample size. I cannot remember it. It will be biased towards that sample. It will have a perfect fit to your sample, but it doesn't mean that it's accurate.
Yeah, I see. Yeah, you're always tied to that original sample and the size. And if you've only got 20, then ultimately you've only got 20. Yeah, I get that. So what are you doing in terms of the next stage of the research? Are you taking this on, or are you doing something else?
So when I published these studies, I was thinking what would be the best next thing. And, I was thinking about impact. And I think the best impact with the results that we got would have been building treatment. And I know, there are great people working on treatments. Probably people have heard from Professor Amy Milton last month. If you haven't watched her talk, I think it's amazing. You should. And we have Nick Zero, his biotech company, working on a new medication. So I thought, what would be the best next thing for me? And I still want to create impact. So I'm still thinking about treatment, because medication, we know it takes some time. And we know that maybe medication might not be for everyone, but also we know that the best treatment outcome is, according to NICE guideline, when you combine both medication and psychological therapy. So my current research is about how we can use AI to make treatment more effective. But it's not just... Sorry.
Yeah. So what, as in literally just asking AI how you can make, can you go into more detail?
Yes.
Obviously it's not that. But
I've been very vague.
Probably on purpose, because you don't want to give anything away. Is that am I delving too far into this, or is it?
No, it's just because I'm also quite early on, so we still need to define the details of it. So I am doing another doctorate in clinical psychology. So I'm training to become a clinical psychologist, and there are competencies that we need to learn. We will be assessed based on these competencies. So the research I'm doing now with my current supervisor at King's College London, we are trying to see how we can train an AI agent, for example, the same competencies that I am learning. And then we are thinking about the things that people can do while they are waiting to receive treatment.
I see. So you're learning therapeutic, as in psychology, you're learning how to do CBT with someone. Mm-hmm. There's a huge waiting list. There's lots of people will know. Some people are waiting for over a year before they get any treatment when they present with OCD. And you're saying that an AI or an app or something could help bridge that gap. And obviously, the better that it gets, the problem is it might put you out of a job. That's the problem, Marjan. But that's the plan. That it would fill that gap.
Yeah, I have to say that what I'm working on is not specific for OCD. It's for all kinds of presentations. Sorry, I forgot what else you asked me. But
just that it would fill the gap for waiting lists. All mental health conditions in the UK, there is a long waiting list, and I'm sure that's the same in lots of countries. Around the world.
Yeah, and we are just because in the context of the doctorate I'm doing now, I wanted to build something that is very comprehensive, but I received the feedback that it's too ambitious for the context of the doctorate. So I'm focusing on a few things that we think can be effective and people can use in the meantime.
Can I take you back to what you were saying about the work you've done with the scanning and the MRS scan to work out the imbalance between glutamate and GABA? So you're saying that people... Oh, were you going to add something?
Can I just make a comment? I remember I wanted to say something and I forgot. You made the comment about me, becoming jobless because of this AI thing. I don't think so. I think we will always need human therapists that are specialized for various reasons. Some people need to talk to a real human, and there are certain things that AI just cannot do because AI has not really lived and felt the way we do.
So when we're thinking about jobs in the future that are safe, probably a therapist is a good one to go into, because lots of other jobs AI is threatening.
I think that would be probably the latest one. And like, if you are more specialized, it will be, you cannot replace those. And the jobs that we already people are using ChatGPT for to write codes and those type of jobs, I think they would be the first. But I think we will be safe.
Fingers crossed. Because I know with presenters, we're gone when AI takes over. They don't need me. So I'm hoping I've retired by that. But you're going to be fine. So when you didn't mention the work that Amy Milton's doing, and we talked to Amy Milton last month. So in a way, we probably could have got the podcast the other way around. Your work is discovering that the glutamate and GABA imbalance in people who present with OCD. And that's about finding out that imbalance. Her work is building on that to see how we can control the glutamate and GABA. And you mentioned Nick Siro. He's trying to raise funds to find a drug that can redress that balance. So correct me if I'm wrong here. Someone who's presenting with OCD, say in the future, we will know that they have a glutamate and GABA imbalance because of what you've discovered. And then we will have some medication that will be able to say, we're going to reset that balance so that it's in balance. And so the OCD, the compulsions aren't as strong. That's effectively, and you're part of that building block to get to that place.
I think so, yeah. In the earlier building blocks.
Yeah. I mean, that's sort of quite key. And we'll see in the years to come how crucial what you've done has been. I mean, it feels very key at the moment, but maybe in the future we will look back on the work that you and Trevor Robbins did in your lab and say that was absolutely fundamental for a very important treatment for OCD. Does that ever sink in that actually you've played a really important role, and it's going to look even bigger as time goes on and more treatments come out because of the work you've done?
I mean, I have to say, because I think we were a big team, and like everyone I work with is so talented and extremely intelligent, and so I did believe that working with a great team, also hopefully leads to great research. And that was when I was doing research, and I would see people with OCD and their families being really helpless, and that was the only thing I could hope for, that this would be the outcome of it. I'm not sure if it has sunk in yet, though.
I mean, I kind of ask a lot of people like you, do you feel like you're doing really important work? And you're all so modest. If you worked in the television world, in media, you'd be saying, yeah, it's me, I'm great. We're all big heads and big egos. But actually, you in the academic world always play it down. But actually, you're doing really important work, and it does make a really big difference. Did you find meeting people with lived experience with OCD that sort of drove you on? And if not, what is the driving factor? What has brought you to this work, to do this work?
So yeah, I have definitely seen many people with OCD, their families. I receive so many emails still to this day from families feeling really helpless. They don't know what else they can do to help their child, from people with OCD themselves. So it has definitely given me the motivation to keep going and to create more impact. But I think what started all of this was having the first-hand experience of different types of mental health problems in my own family. So as a child, I could see the negative impact that the mental health problem can have on the whole family system. So I was always curious about, how do these negative outcomes happen? Why do some people develop mental health problems? What's happening in their brain, and how can that change? Can we change something about the brain to change that? Can we change something about the behavior to change the brain? So I was always curious about that. So that led me to study psychology and neuroscience, PhD in cognitive neuroscience, and now a clinical psychology. But the reason I'm studying OCD, I started studying OCD specifically, was because, the moment I found out what the role of the frontal regions of the brain is, so like all these areas, and for example, the SMA, supplementary motor area, that they are the control seat of the brain. So I was curious to study these regions. And I decided to study obsessive-compulsive disorder because we knew that these regions have deficit in OCD. That was the start of it, but I have become very much, I don't know, it's also an emotional problem now, because I've been heartbroken so often that I really feel I need to do something. It gives meaning to the work that I'm doing if I'm, finding impactful. I don't know, if my research leads to impact on the treatment for OCD.
Yeah, and I mean, I guess in some ways, academia and academic work is far, in some ways, far removed, because the work that you do might get the treatment in 10 years' time that people who are with lived experience of OCD will experience. So
Yeah.
there's a long gap. It took you 3 and 4 years to do what you do, but it's absolutely crucial in laying the foundations for perhaps something that will change people's lives in the future. And there'll be people listening to this who will be despairing. And I know it can be really debilitating. It can ruin families. It can be so hard. So it's really important that you do the work you do. In 10 years' time, maybe 50 years' time, can you sort of tell us where you'd like to see OCD treatment, where perhaps building on the work that you've done, where we'll be in 10 years' time, where we'll be in 50 years' time? I mean, I don't think I'll be here in 50 years' time, but what do you think the state of OCD treatment will be?
But I'm really bad at planning and these type of things, but I can think about the ideal scenario and what my dream would be.
This is the dream, so you can
This
say
is the
whatever you
dream.
like.
Yeah.
And then in 10 years' time, we'll get you back on and we'll say, you said this. No, we won't. Don't worry.
And I hope it happens less than 10 years. I hope it happens maybe in 5 years. So I'm really hoping that everyone will get an individualized treatment according to their needs, whatever their need would be, whether it's medication, whether it's neuromodulation, when like about TMS, for example, which is non-invasive treatments, whether it's psychological treatment or new types of treatments that we cannot even imagine right now. And for treatment to be accessible to everyone. And for people to find out they have OCD as soon as they start showing symptoms, because I know so many people suffer for many years. I think the average time for diagnosis is about 12 years, and the average time until people start receiving their first treatment is 17 years. So if you can imagine, an OCD starts, for many people during childhood, it really impacts someone's future if they cannot study, if they cannot go to university, if they cannot find, someone to get married to. Like, it impacts the whole family and waiting so long. So I think the dream would be getting the help they need as fast as possible and individualized.
Yeah, and that's what we're doing. That ties in really well, your message there, with what we're doing or aiming to do with Orchard.
Yeah.
Give clinicians an armory of medications and treatments, and other treatments, doesn't have to be medication, so that at the moment, and has been the case for so many years, the go-to is SSRIs and CBT coupled with it, which works for some people. Well, it works for many people, but it doesn't work for everyone. And that's what we're trying to do with Orchard. So someone presents and you will be able to have an individualized treatment that, that works for you, but this one works for you, and this other one works for this person. In the same way that cancer treatment has become a lot more individualized and a lot more technical than it was, say, 30 years ago. And it doesn't feel like that has happened in OCD. And you are playing a key role in that, Marjan. So thank you very much. And we've come to the end of our hour. So thank you very much for speaking to us and giving us an amazing insight into the work you've done, and this fantastic work that, as I say, it looks like it's going to be the building block for something really special for people who have lived experience of OCD. Marjan, thank you very much. Thank you very much for everybody for watching and sending in your questions. Marjan, thank you. And we'll see everybody again, I say in a month's time, well, next month, but next month is tomorrow, isn't it? So in August, we will have another OCD Conversations. We'll be speaking to another person just as interesting as Marjan. So we'll see you then. And thanks once again, Marjan.
Thank you. Bye.